In this video, we are going to look at applications of dynamic programming and greedy algorithms in graph algorithms. In particular, we are going to look at shortest path problems. Okay, so first, let's look at what algorithms we're going to study. In particular, what problems we're going to look at. So suppose we have a graph G. So you have a set of vertices V and a set of edges E. So we assume this graph. We assume that this graph as a weighted and directed graph. Okay, weighted means that each edge has a weight, which is a numerical value, and directed means that each edge has a direction. All right. So what that means is that suppose I have an edge, and then this edge has a direction. This means that from node U or vertex U to a node V. And on this edge has a weight. We can write it as WUV, indicates that it is a weight on this edge, and this weight is a numeric value, which could be 0, which could be positive, and also which could be negative. Okay, so that is a weighted and directed graph. And when we also use DAG as a shorthand for directed acyclic graph. Okay, so which means that this is a directed graph, and this graph has no cycles. And then when we say a graph is dense, if the number of edges m is in the order of n squared. Okay, so this is that means that a dense graph has a lot of edges. We know that a complete graph has this many edges. Right, a complete graph has n choose too many edges, which is equal to n times n minus 1 over 2, which is in the order of n squared. So this is the maximum number of edges a graph could have. Okay, so, and for any smaller constants, okay, as long as it is in the order of n squared, then we're going to say it is a dense graph. So as what we are going to do here is that we're going to use dynamic programming and greedy strategies and traversing, graph traversal to find shortest path. So these are common techniques for graph algorithms. What we're going to look at is two types. One is we're going to find single source shortest path. So what that means here is that, say you have a graph. Let's say I have, this is my graph G, and then I have a single source node S, and then it has all the other nodes. And we are going to find shortest path from S to all the other nodes. So this is a single source shortest path. In particular, we're going to look at two algorithms. One is Dijkstra's algorithm, the other one is Bellman Ford. Dijkstra's algorithm is a greedy algorithm, and it can only work on graphs with non-negative weights. Okay, but it is the fastest algorithm for finding single source shortest path. It is an n log n plus m algorithm. M is the number of edges, and Bellman Ford is a dynamic programming algorithm, and the good thing about this is it allows negative weights and negative weight cycles. And the algorithm, the runtime of the algorithm is in the order of n times m. Okay, so v times e. And the second problem we're going to look at is all pairs shortest paths. Okay, of course, we can use a single source shortest path to solve this problem by going through all vertices. And for each vertex, we are going to look at we are going to find single source shortest path. But of course, it is not necessary. And so this algorithm will be time consuming. So it's better to just look at these, or to find all pairs shortest paths differently. So we have a Floyd-Warshaw algorithm. It is a dynamic programming algorithm. And it allows negative weights, but it does not allow negative weight cycles. And then we have a Johnson algorithm, which is Bellman Ford plus Dijkstra. Okay, so it allows negative weights and it allows negative weight cycles also. In terms of running time, Floyd-Warshaw algorithm is in the order of n cubed. N here is the number of nodes, or v cubed. And Johnson's algorithm is in the order of m squared log m plus n m. So this m is just e, number of edges. Okay, e squared log e plus ve. Okay. Now let's first look at single source shortest path. We are going to find the shortest path in G. Again, this is a directed weighted graph from a given source vertex to all other sources, or to all other vertices in the graph. This problem has many applications. For example, it can be used in transportation planning. So you start from one place, you want to visit many other places, and then you want to find the most suitable routes, either the cheapest or shortest time, right? That kind of things. And of course, it can also be used in packet routing, in data communications, or in communication networks, or friend discovery in social networking, single friend recommendations in Facebook. Okay, so you have links between friends and recommendations. You could think of it as weights. And of course, we can also be used in speech recognition. In other words, this problem has many applications in different areas. So first we try to formulate this problem. So this problem can be formally described as follows. So first, the input is The input is a weighted directed graph and a source vertex, or source node S. And the output is the set of shortest passes from S to all the other nodes. So this is the single source, and V is all the other nodes in V. Okay, so we want to find it. We want to find this. So now let's look at greedy Dijkstra's algorithm. This is for finding single source shortest path. So we let G be a directed and weighted graph without negative weights. So all the weights have to be positive. And the algorithm is simple. So let's just look at this. Let's just look at pseudocode. So initially, we are going to, so for each node, let us say this is my graph. Okay, for each node, say this is my S. Okay, so we are going to assign two fields to each node. One is to remember its distance from S. So this is distance. The other one is a link to its predecessors, and that is called pi. So this is remember where it comes from, its predecessor. A link to okay, a link to the node that it comes from. So then initially we're going to set initially we're going to set the distance, of course, from the source node to itself is 0. And then for all the other nodes, we're going to say that distance at the beginning is, we set a very large number. So this is very large positive, very large number. And then because we don't know where it comes from yet, so we're going to say that order its link to its predecessor is nil. So then we're going to look for all the neighboring nodes of S. Okay, we're gonna look at all of these nodes. Okay, so and then we're gonna use a greedy algorithm to select a node that we're going to put into my solution set. So we're gonna let S be our set of nodes that we selected. So initially it is empty. Okay, so this is the initialization. So initially S is empty, and then we are going to put all the nodes in this priority queue. So this queue here is a priority queue. And we're going to select a node each time from queue and place it into S. So how we're going to select it, we are going to select the one with the minimum distance. Okay, because each node has a node D. So we're going to select that node. So initially, of course, all the other node has a very large D value, and only S has 0. So that means initially S is selected because it is 0. Okay, and then we are going to place this S into this solution. Place this S into this solution. And then for all the neighboring nodes, which means that there is an edge coming from S. Okay, so for all those nodes, we are going to check because it has a weight. So we got weight. Of course, obviously, we want to select the node that has the minimum weight. So that is this, okay? So for all the adjacent nodes of U, which has not been selected, so this just means that which has not been selected yet, still in queue, which has not been extracted yet, okay? So that it's in queue. And we're gonna check. We're gonna say this is U dot D plus WUV, okay? So which means that you're coming here, so let's call this U, and you have all these other nodes directly connected from U. So let's say this V1, V2, V3. So at this time, I have a U dot D value, because initially this is S, that's 0. And let's call this W1. W2, W3. So from U, you can go to V1, V2, or V3. So this is V. So using greedy algorithm, you know what you want to pick. So we want to pick the one with the smallest W's, which means that if V dot D is greater than U dot D plus W, then you are going to change that value. Okay, each of these values we are going to change it. So at the beginning, this is a infinity, of course. This very large value, which is greater than this. So then it has a new value D. Okay, so you update this D as long as it is greater than where it comes from. It comes from U. If it's greater than this, then you change that value. And then using this priority queue, the next one you're going to select is the one with the smallest weight. For instance, if W1 is the smallest, then the next one you're going to select is this. So that's it. So until you don't have any nodes left in queue. So that's Dijkstra's algorithm. Straightforward, and but it works. Okay, it gives you the shortest path. So now let's look at an example. Okay, so given here is a directed weighted graph. Okay, so we have this weight on each edge, and each edge has a direction. Initially, we set the D value for each node. Okay, so this is the single source, that's 0. All the other nodes is set to a very large number. So we use infinity to represent it. And then we pick, okay, we put all these nodes in a priority queue. And then, of course, the smallest D value is S, so that's selected. So it's selected. And then for this node, we're going to look at all its adjacent nodes, which is T and V, so T and V. And we are going to update its D value. Okay, so here it comes from this, and this is 10, this is 5. Okay, so next time we're going to select is this node because this now has removed from Q. So what's left is 5, 10. Sorry, what's left is Y, T, X, Z. So then, of course, this Y is 5, so it's the smallest. So we're gonna pick that one. So once you are here, then we're gonna look at all its neighboring adjacency node, which means it can go from 5 to directly to the nodes that can come from 5. So all the other nodes can come from it. So 7, 4, I'm sorry, Z, X, and T. So now we're going to update its value. So Z is infinity. So then of course it's greater than 5 plus 2. So then of course we use 5 plus 2 as its value. That's 7. And this, okay, can come from here. And this, the value D is 10. But 5 plus 3 is 8. 8 is smaller. So you're going to update that 10 to 8 because coming from 5 is shorter. So you put 8 there. And then this is infinity, of course, that is 9 plus 5, that is 14. So then 5 is removed. What's left is 7, 8, 14. So the smallest one is 7, so 7 is selected. And then you look at its path. So you look at it's just adjacent nodes. Look at the nodes that can come from 7. So 13 is the only one. Okay, so from 7. So 13 is, this 0 is already taken out, right? So then, of course, you change. So that's 14, okay? But from 7, if you come from 7, so from Z, sorry, come from Z, so that's 7 plus 6, that's 13. 13 is smaller, you update that distance value. Then, of course, the 7 is removed. So what's left is T and X, so these two nodes. So this is the smallest, you pick that. And then from 8, you can go to 5, but 5 is already removed. So that's the only one, that's 13. And 13, that's X, okay, that's X. And then the value here is 13, but then 8 plus 1 is smaller. So then you change that to 9. 8 plus 1 is 9. So then you're done because all the nodes has been removed. However, of course, so what we are showing here is the only update is a D value, but you should also update its predecessor. Okay, so these this shaded edge, okay, is indicating its predecessor. Okay, so T and 5, so predecessor 0, so you indicate its predecessor. And then here, 7 comes from 5, so it's the predecessor. And 14 comes from 5, 8 comes from 5, so it's a predecessor. But then for instance, for this 13, for this node X, it's up. So because it changed, it's no longer use 5 as a predecessor because this path is shorter. So you change its predecessor of 13 to of X to Z, right? So that is Dijkstra's. Now we need to show, as we said when we talk about, as we said in previous video, that when we use greedy algorithm, we need to show that the greedy choice works. Okay, so we need to prove it. So here we're going to show that that greedy choice works. Okay, so this is a theorem. For any node U, which is added to S by Dijkstra's, must have, so when it is added to Dijkstra, or when it's added to S by Dijkstra, we must have this. U dot D is equal to delta SU. This is, here's the delta U is the length of the shortest path from S to U. Okay, so this is what we need to do. So in other words, once it is put into S, we no longer need to visit it. So it has the shortest path from S to U. So that's what we need to prove. So to prove greedy choice, to prove that greedy choice works, we usually use proof by contradiction. Okay, so by contradiction means that there is a node U that when it's added to capital S, its D value is not equal to delta S dot U, so which means that it will have to be greater than it. Okay, so by contradiction, so let U be the first node, because there is such node, there may be more than one, but we can always say we can pick the first one that's added to S. Okay, so we pick U B to be the first node chosen to be added to S, but its distance is greater than the shortest path, the length of the shortest path from S to U. So then we're going to say this is impossible. We're going to prove that it is impossible. So we consider the case just before U is added to S. This is the first one. So before it is added, that means that for all V, okay, V dot D is greater than or equal to delta S V. That's the first thing, okay? And then let P be the shortest path from S to U. Then first of all, such path exists because U is added to S, okay? So you can only add this node to S if there is a path from S. And S cannot be empty before U is selected because the first one is selected is a small s, the single source, okay? So the single source, the distance is 0, okay? So that one is already selected. So when this one is true, then of course, this s cannot be empty before U is selected because the single source is already there. And then every node X placed to S before U must satisfy this because we're saying that U is the first node chosen to be added to S that violates this condition. So that means any node selected to S before U is placed into S must have this property. Okay, so now let's look at so then that Y be the first node that is not in S. That's not in S, but it's on this path, the shortest path, shortest path. Okay, be an edge on P, and because P is shortest, okay, so so this Y, okay, this Y is the first node on the shortest path, which is P from S to Y, okay, so then Y cannot be, no, that Y cannot be U because P is shortest and U does not have that property, okay, so it's not the shortest. So U is not the shortest. So that means that we have, because it's the shortest, so Y dot D is equal to the actual distance is equal to delta S comma X. Okay, so this is the shortest. And we know that its D value is equal to this plus that, okay, because this x is already in S and it is shortest, so that its d value is this. And then because y is added, it's on the shortest path. So then, of course, its d value will have to be equal to this one plus delta plus that, and actually that is the shortest path. Because by assumption, this is the shortest path. All right, so now let's look at this explanation here. So we have this shortest path, okay? And then this u, when u is about to, so when u is added to S, okay, it violates the condition. So it does not have, so this ud this ud is greater than the length of the shortest path from S to U. And what we want to show, it is impossible. So what we're going to say here is that, so U is the first one that has this, that violates this condition. And we also know that U cannot be the first node selected. So in other words, when U is selected, its a previous capital S is not empty. So that means you may have a node X. This X could be S, but that's okay. So in other words, for this node X, we have that X dot D, X dot D is equal to delta X. Okay, we have that. And then we have this shortest path to U, and then Y would be the one that's directly connected to X. Okay, so this is on the shortest path. So then we know YD is equal because this comes from X. This is shortest. So we know YD, we change its value to, which is equal to XD plus W XY. And then we know XD is equal to delta S comma X. So this W XY. Okay, so that's what we have. And then this will be, it is on the, this Y is the shortest. Okay, because we assume that Y is the first node on P. Okay, and XY is an edge on P. So that means we would have, this is equal to delta S this is equal to delta SY. All right, so now, so hence we have this delta SU, you will see this, which is equal to delta SY, you go to here, and then plus delta Y to U, so this part. And this is Y dot D, and this is Y to U, and from Y to U, so this part cannot be empty. Remember, the weight has to be positive. Okay, so this weight here is positive. So that means that, I'm sorry, the weight cannot be negative, sorry. So this P cannot be negative. So which means that it will have to be greater than or equal to 0. So that means this is greater than or equal to Y dot D. Hence, U should have not been chosen because by So you should have select Y before U is selected. So U should not be chosen. So which is a contradiction. Okay, so the runtime of this algorithm, if you just look at priority queue, and so you maintain a priority queue for all the nodes that is V log V because it needs sorting, and as you see here, for each node, you're going to look at its neighboring nodes. You're going to look at all of these. You're going to update its value. So it looks like it would be for each node you have these many nodes. So in the worst case, you're going to update this many times for each node. You're going to look at them. Plus sorting. So this is sorting. But then using a Fibonacci heap, okay, you can do slightly better. So instead of V square, we can change this part to E. Okay, so that's slightly better. Of course, if it is dense, if the graph is dense, it's about the same. Otherwise, it would be better. Okay, so that's Dijkstra's algorithm. Okay, now let's give a review for this proof. Let me open up a new screen. Okay, so we want to prove now once again, Dijkstra's algorithm is like this. For any node U, and you're going to look at its adjacent nodes. Let's call it V1, V2, VK. Okay, they have this D value. So each VI has this D value. So we update the D value, and then the next time we're going to choose the one that with the smallest D value. So once we choose, we are going to place them into S, and that's done. So what we want to show here is that whenever we place a node U in S, we must have delta SU is equal to U dot D. Okay, its distance must be the shortest distance from S to U. So this is how we're gonna say that greedy choice works. So we prove it by contradiction. So what that means that if there is a S, there is a node U that's added to capital S, that violate this condition. So that means that its distance is going to be greater than the length of the shortest path from S to U, right? Because it cannot be the other direction, because its value is starting from infinity, so it gradually reduced. So of course it's always greater than or equal to delta S comma U. Right, so we know for any node that's greater than or equal to that. So if it's not equal, then it can only be greater. So that looks like this. Okay, so this U be the first one. So this is the first one to be added to S. So then we are going to say we let P be the shortest path. or one shortest path from S to U. Then we're going to look at on this path. Okay, since we know that the U is the first node to be added to S that has this condition. That means any node before U that's added to S must have, so any node, let's say up to here, any node X added to capital S must have X D delta S X. Okay, so here is what S is. And of course, this X could be S because S, it has its value. We know S D is 0, which of course is delta S to S. There is no, so this is always hold. So then what we're going to say here is that we let Y be, so let Y be a node on X. So be a Y node on P, and it's a direct link from X to Y. Okay, because so P is the shortest, so that means from S to X to Y. So this portion is also shortest. Okay, if it's not shortest, then of course you can find another, you can replace this into P, then of course that violates the assumption that P is the shortest. Okay, so this is the shortest. So then because it is shortest, what we have, so what we have then is that and Y here is YB. So in order, so we update this YB value, of course it will be from X P plus W X Y. And because it is on the shortest path, we know it is the shortest, so it is equal to delta S Y. Okay, so that means this Y cannot be U. Okay, this Y cannot be U because we know U is this. So that means there is from U, so the distance from Y to U, so this is shortest distance, it is greater than or equal to 0. Could be just a direct link. So now we're going to say that delta so now again, this is a path, but it could possible that from, since Y is not U, so it could possible from X to U, there is another link directly connected to it. So, but then for this, okay, so we're going to say from S going through this path to U cannot be the shortest. So in other words, there will be a contradiction. So what we are showing here is that U dot D, suppose it could come from So its distance value is from u dot y, I'm sorry, so y dot d. So that's one way, okay? Plus delta y to u, and this is greater than or equal to so let me erase some of these. Do it again. So we know that d is greater than delta s u, and this is equal to delta s y plus delta y u, and this is y dot d. And this is greater than or equal to 0. So that's greater than or equal to y dot d. So in other words, is u dot d is greater than y dot d. So this x is the node that's placed into S before u did. But then we are seeing, we look at this y dot d. Y dot d is next to x. And this u, okay, u dot d may be next to some other things, so may not be from x, right? So this may be another node. Okay. We just picked the one with the smallest d value, right? But that's in S. But then, of course, this one will not be picked. Let me remove this, right? So u dot d is greater than y dot d. So then, of course, y dot d should be picked before u. Okay, so so then you're saying that this is step u is selected is wrong. Okay, so this is wrong. So that's a contradiction. Okay, so there are some subtleties in this proof, but if you think about it more carefully, then you get the idea. So now let's move back. Okay, now let's look at Bellman Ford. So this is a dynamic programming technique. So we can use dynamic programming technique to find single source or single source or shortest path, right? So that so we can formulate this problem as following. So that delta S comma V denote the weight of the shortest path from S to V. And the summation of weights on each edge of the path is delta. So that's what it is, okay? So we want to formulate, we want to come up with a recurrence relation. So the shortest path can be divided into smaller problems. So which is sorry from S. Say this is a path to V. Of course, you can say this is S to let's call this T, and then T to V. If we change this S to U, that would be in general. So if we can define delta UV, which is for some T in between on this path, which is delta UT and then T to V. And So this, so how many t's we have? So the in degree of, so this is in degree of v, okay? So which means that how many t? So this t here, so it's t1, maybe t2, maybe there's some other t here, right? So that means that for any t that directly goes to v, we want to select the one that has the smallest weights, okay? So which means from s to t plus tw, that's the smallest. So that's min. Okay, so if s to v, that's 0. Otherwise, it's equal to s to t and then plus wtv for the smallest such value for t. So that is the recurrence relation. Okay, so far so good looks like, but we have some issue here. So for instance, if this p is acyclic, there would be no issue, right? So if the p is acyclic, then this works. But what happens if your p is cyclic, it has cycle, then it will not work. Okay, so let's see a counter example. Okay. So let's say we have an example that has a cycle, right? So we have a cycle here. Then what we could end up would be, in this case, so SV, which would be SU directly UV, and then in this case, okay, so SV, okay, so the SV would be equal, so what's the path? We'll go here, go there, that will be SU and then UV. So that's what we have, SU, UV. And then this SU, go back here, SU going to ST and TU, right? ST and TU. So ST and TU. So of course we still have this plus. So this SU becomes that one. Okay, so that's how we go into about SU. Then ST, so ST will be SSST, right? So that's this. And then TU will be, now see that TU, so how do we get this? So TU could be, there's a cycle. So TU could be from here, it's from SV to VT. So sorry, this ST, okay, ST, no, look at this ST, not this, okay, only on delta. ST could be going this way. It could go SU and then see going to ST. ST will be SV, okay, going here, going there, SV, and then VT, okay, going there. So that means that it has a cycle, it goes back. So it goes back to XV. So it's like Skype it will loop. It will loop if this distance value is negative, then you can keep looping and get a smaller and smaller value. So it's not going to work. So then, how can we fix it? So to fix it, we consider the following observation. So if a graph doesn't have a negative edges, then the shortest path must contain no cycle. So in other words, any shortest path must be a simple path. And the maximum number of edges in the shortest path is the number of nodes minus 1. Okay. So that is the number of edges. Okay, that's easy to see. So this is the upper bound, because the number of edges on any path. Now this is a simple path. Okay, so that means it can only be a v minus 1. And then, so what we're going to do here is that to construct a dynamic programming whose recursion tree is steps limited by the maximum number of edges, so that we don't allow the depths to loop forever. So then to fix it, so we put this restriction, the length of your path related k. So let delta k as v be the minimum weight path from S to V, such that its length is less than or equal to k. So this k has upper bound v minus 1. And then the rest of it is the same. So if k is equal to 0 or s is equal to v, then it's 0. Otherwise, it will be coming from a shorter path, not coming from a longer path, right? From a shorter path, k minus 1. It's just similar to what we had earlier. Then what we really want to compute is delta v minus 1 SV. So then the dynamic program would work. So it's a Bellman Ford algorithm. So it is a version of it. So the version is just use memorization to carry out this recurrence relation. So we already saw this technique before. It is still recurrence relation. We use a memorization array to remember the results we computed earlier for some problems, so that we don't have to recompute them when we need them. Okay, so the runtime in this case is just the, you look at the recurrence relation. Okay, so how many such edges? E many, okay, and the length. Okay, so how many lengths? So that's a V, so that is V times number of edges. Okay, so that is the runtime. All right. Okay, so now we look at a Bellman Ford in the setting of Dijkstra. Okay, so here is still the same as Dijkstra's algorithm, but now we only for the loop we only look at. So this is a look for each path. So I from 1 to g dot v minus 1. So for each edge, if v dot d is greater than u dot d plus w, we update its value. And then The U is a predecessor. Okay. So now dicers, of course, we don't have this loop. Instead, we always pick the node because that's the greedy algorithm. So we always pick the node with the smallest d value. But in this case, we just check for all the d value, we're going to check, we change it. So then we're saying that for each edge, after we finish this loop, if v dot d is greater than u dot d plus w uv, we return false. Otherwise, we return true. And then we can show that this algorithm returns true if and only if this graph contains no negative weight cycle. That is reachable from S, okay? That's reachable. Now remember, it may still have a negative weight cycle, but it's not reachable. Reachable means that that cycle can be reached by starting from S, right? You think of it, you do a walk on this path or traverse. You traverse this graph, then you have a path from S to this negative weight cycle that's reachable from S. Okay, so here is a proof why that works. Okay, so if G contains no negative weight cycle reachable from S, then for all V, for all node, when Bellman Ford terminates, we have this value. So this is a proof, okay? So this is a induction proof. So intuitively, it's pretty straightforward because we are going to always keep updating this. Now, this is different from dicers. Dicers, once you update, so once a node is placed into set S, you removed it because that's done. It's greedy, it's done. And that, if you don't have a negative weight cycle, negative weights, that works. But here, we always, so we are going to loop this many times. So each time we're going to look for all the edges and update its value, update its d value for all the edges. Okay, so that's what we do. So if there is no negative weight cycle reachable from S, then eventually its d value is going to be equal to S comma V, since you do it for V minus 1 times. So all the paths will have to be, all the edges and on all the paths will have to be looked at it. Okay, so this is induction proof. So let P be a shortest path from S to V with the length of P be K. Could be smaller than V minus 1, but V minus 1 is the upper bound. So if the length is 0, that means this V is S itself, is trivial. So suppose that when P, the length of P is equal to K minus 1, this statement is true. So which means this is true. Then that U be the predecessor of V on P. So that means U dot D, so it's a predecessor. So this is U V S. So the whole path is K, then from S to U is K minus 1. So, okay. So then, of course, we know from by hypothesis, U dot D is equal to delta SU. Right, so this is by hypothesis. And then, so then V dot D in here will be equal to V dot U, I'm sorry, U dot D plus W UV. Now remember, this is the shortest path. And since U dot T is equal to delta SU plus WUV, it is delta SV, okay? Because it's on the shortest path. So the proof here, when G contains no negative wave cycle reachable from S is straightforward. Otherwise, we're going to say that it will return false. In other words, this will not be satisfied. So, so this is return true, right? So at termination, this is return true. Otherwise, if there is a negative wave cycle, that's reachable from S. Okay, so we let this be a cycle. Okay, so this is a loop where Vk is equal to V0, and then you sum all the way is less than 0. So then if Bellman Ford returns true, then it means that for all edges on this cycle, we have this, because that it's what we're going to check, right? So only when it's greater than, it returns false. So if it's returned true, that means less than or equal to this. Hence, we're going to look at its weights, okay, on this path, on this loop. So that's less than or equal to this. So you do a summation, a manipulation, so you separate it, so that is Vi minus 1 dot D, I from 1 to K, plus I, so this is Vi minus 1 to Vi. So now let's look at this here. So we know that when I is equal to 1, Vi minus 1 is 0. We know V0 is equal to Vk. Okay, so that really means that I can replace V0 with Vk. Okay, so that means that I can have Vi, so because V0 being is replaced Vk, so this I could just go from 1 to K. So Vi from 1 to K. Okay, so that means these two are equal. So that means you remove this, we get this part greater than or equal to 0. That's contradiction because it's a negative wave cycle, so it cannot happen. All right. Now we're going to look at Floyd-Warshall algorithm, which is which finds all pairs shortest paths without negative cycles. Okay, so in other words, suppose you have a graph G that does not have negative cycles, then we can find all pairs shortest paths using Floyd-Warshall using dynamic programming. So again, as we said, dynamic programming, we first set up the names and parameters, and then we're going to come up with a recurrence relation. So we let Dijk be the weight of shortest paths from node I to node J, where all intermediate nodes on the path are a subset of from 1 to K. Okay, so of course we know that we have 3 parameters and each of them can go from 1 to n, so there are n cube subproblems in the order of n cube. So what we want to compute is Dijn for all pairs ij. So that we come up with a recurrence relation as follows. So for any I and any j, we look at the value of k. So if k is 0, that means it is just itself. It doesn't go through any intermediate nodes. So that's wij. That's the edge itself. Otherwise, if it's k greater than or equal to 1, so we can say that dij can go k minus 1 without going to k, or you have to have an intermediate node k, because if you go through k, and then from I to k, you only go through intermediate nodes from 1 to k minus 1, and also from k to j is k minus 1. So these two, whichever is smaller, we're going to select it so that it's a minimum of these two for any, if k greater than or equal to 1. Okay, so we can use a memorization technique, and that's a standard technique for solving dynamic programming problem. And for this, we can actually use bottom-up by getting rid of recurrence relation. Okay, so using loops. Okay, so initially, D0 is all the weights for the adjacency graph, and then for k from 1 to n, we let dk be dijk, and dijk is computed by this loop. Okay, so k1 to n. So in order to compute this, it is just equal to dijk minus 1, ikk minus 1, because initially we have this 0. When k is equal to 1, k minus 1 is 0. So that is just its weights. Okay, so then you loop this, then you can compute all the dijk up to n. So dn then is your output. All right. So actually, when you don't have a negative weights, it is a finding all shortest paths, all pairs. Okay, all pair shortest paths using Floyd-Warsaw is an efficient method. Then just using single source, and you repeat single source algorithm. Okay. Here is the shortest path construction. So again, this is a simple technique. So we just remember when we set the value, so then we just remember where its predecessor is. So we have looked at applications of dynamic programming and greedy algorithms to find shortest paths on a weighted directed graph. So the difference here is that given a graph, whether it has negative weights, whether it has a reachable negative weight cycles, or it does not have negative weight cycles, or whether we want to find single source shortest paths, or finding all pairs shortest paths. Okay, finding all pairs shortest paths without negative weight cycles, we use Floyd-Warsaw algorithm. If there is no negative weights, okay, then Dijkstra's algorithm, finding single source, is the fastest. But Bellman Ford can be used to find single source shortest path in the most general case. Okay, so we can actually determine whether there is a negative weight cycle reachable from the single source from S. Okay, so So that is some of the differences. So now let's look at transitive closure. We want to determine if G contains a path from I to J for all pairs, ij. So which means that whether J is reachable from I, so we can do a matrix computation to find that out. So define a transitive closure of G as the graph G star, where if there is a path from I to J, then that is an edge in E star. So then this is, you just keep multiply this adjacency matrix. Okay, so initially we let Tij 0. If ij is not an edge, is 0. Otherwise, its edge is 1. And then we keep doing this, right? So Tijk will be either Tij k minus 1 or Tik k minus 1 and Tkj k minus 1. So if this is 1, then it's 1. If it's not, if this is 1, then it's 1. Okay, and it just matrix application, multiplication. So initially it's just adjacency matrix, and T1 would be okay, so actually you could think of this or would be a plus modular, so it's just plus. So or is just plus, but modular 2, and this n is just multiplication. Okay, so what that means here is that you multiply a new matrix. So for instance, okay, so because T1 is just T0, and let's say T2, so how do you get T2? So T2 is just T1 times T1, right? So you think of T1, so T1 is times T1, so that is 1, 0, 0, 0 now. And then this going here, you get 1. Now, as long as there's a 1, that's 1, right? So here, there's a 1, 1, 1. So here, going there, that's 0, right? And then going there, there's a 1, so that's 1. Going there, that's 1, and that going the last one, so this and that's 1, so you get 1 there, right? So it's just multiplication. And then T3 is T1 times T2. T4, you could either T1 times T3 or T2 times T2, and you add them together. Okay, so that is transitive closure. So last, we're going to look at Johnson's algorithm by reweighting a graph. So what we're going to get is a non-negative weight edge while preserving shortest path. So, so we are using the following. So you have, let's say you have a negative weight. So when you have a negative weight, then you won't be able to use Dijkstra's algorithm. If somehow I can change negative weight to positive while preserving shortest path, then of course we can use Dijkstra's algorithm. So here is a technique to reweight a graph. So what we're going to do is for any function h, okay, so h is the function, we're going to let a new weight w hat uv, which is the original weight plus hu minus hv. So let's p be any path from v0 to vk. Then we add the weight on this path. Okay, so which is equal to, now there's a new weight which is equal to this. Okay, so this portion gets out is vp, and the rest of it in the middle one is cancelled. So what we get is the beginning and the end. So that's v0 and vk. So hv0 minus hvk. So if this new way is the smallest among all paths from v0 to vk, then of course, if and only if this is also smallest under the old weight, because this h is fixed and v0 and vk is also a path, the beginning node and the ending node. So this h is fixed, so this is the smallest if and only if this is the smallest. So that's how we reweight. So now we are going to add a dummy node s to every node u with its SUB0. And then what we're going to let, so we let h of u be delta SU. Okay, so this is the function h we're going to get. So then by triangle inequality, we know that delta SV is less than or equal to delta SU plus UV. So this is a direct edge. Hence, you add them up. Hence you get W hat UV, which is WUV plus HU minus HV. And so this is equal to, now if you see this, WUV is greater than or equal to delta SV minus SU. Okay, so then that is, so let me just write that on here. So from here, we get W UV plus delta SU minus delta SV, which is W, no, this is greater than or equal to 0, right? So this is greater than or equal to 0. And this is HU, and this is HB. So that means the new way is greater than or equal to 0. So the question is, how do we find delta SU? Well, we use Bellman Ford to do it. If it has a negative weight. Okay, so then Johnson is we first use Bellman Ford to compute all delta, and if it returns false, then we just print there is a negative weight cycle. Otherwise, if it's returned true, then we use reweighting, so reweight every edge, and then use Dijkstra's algorithm to find a shortest path from this new node S to all the other nodes. Okay. Yeah. So for each U, then we use this to compute all the other nodes. Okay, so this S is we use Bellman Ford to compute all the the shortest path from this S to all the other nodes, and then for each U, because now there is no negative rate cycle, then we can use Dicer's. Because now there is no negative weight, then we can use Dicer's algorithm. So that's Johnson's algorithm, and the runtime is Bellman Ford is V, okay, and then is for each node V. You do a Dicer's once, that's V log V, so that's V squared log V. Okay. So that is the end of this video.